Okay, so let's start the class by talking about this. So yeah, talking about network design course. Good. Here we are talking about network design. As I mentioned, in the network design, the general idea is that this is some network. Network is just a graph essentially, and on top of that, we have more conditions, more properties, more motivations essentially, like that we will considering for these problems. And generally, the edges, for example, they have more properties, and these are not just simple edge connecting these two, but they have some traffic, they have a cost to buy, they have, if you want to send the traffic, how much would be the cost, and lots of these things. And the same thing for the like nodes as well. You can think about the nodes as the routers, and the edge is the communication fiber network or fiber edges between them. Good. And this has like applications all over the place. Some of these applications you have seen uh, or we have seen in the communication networks before. There are lots of places like AT&T or Verizon and others. They were actually, telecommunication was a very hot topic like before 2000. And then after that, these tech companies came and then they took over. But in some sense, they didn't. I mean, still the same thing is there because Google actually had, now actually Google also went to the business of Google Fi for wireless because they want to have the people on their network essentially, because then they can, it was some net neutrality fact and rule that, I mean, the people like for example something like AT&T or Verizon, they couldn't charge for the traffic which is inside their pipes essentially. It should be net neutral. It means that if some traffic is going there, you should not charge based on who is sending this traffic. You cannot charge differently. Should be, so it's kind of pipes. In this pipe, anything that goes inside, you should not charge based on that. This was essentially ruled out several years ago, and then now actually it's charging. Now, for example, if you have a Verizon network at home and then you are seeing Netflix, then Netflix should pay something. They have some agreement between Netflix and Verizon that they will pay some part of the money that Netflix gets it essentially to Verizon. Because otherwise all the money went essentially to tech companies and these others were just carrier without anything. So that's the thing that they wanted to get rid of this rule essentially. And this rule was not for wireless, that was for wired only. For wireless. And I mean, then essentially they don't have that rule that much now, essentially, and they can charge it. Still, there are some, I mean, maybe conditions or something, but other than that, there is they can charge it essentially. So and now this, but at the same time, I mean. Some companies like Google, for example, they are creating these networks now between the GPUs. So they have a very big, essentially, GPU network of. Before it was like computers that you were making. Now they are between for GPUs that they are making such kind of infrastructure, such that they can talk fast with each other, and then they can do some kind of problem, some of this deep network stuff, or in particular LLM, large language models, essentially effectively. Good. And so here we are talking about, I mean, lots of network algorithms, which are essentially graph algorithms and beyond. And you will see lots of nice techniques essentially in this class. We talk about lots of things about approximation algorithms, and in particular, the places that, uh, like you can see also this class somehow about approximation algorithm, but more focused on network design. And some of the techniques, these are beautiful techniques that the people have designed, but maybe more recently the people looked at it less. So that's the thing that is good essentially to know about this knowledge and potentially use the approaches for new problems. Good. So let's talk about these ones. Good. So here we are talking about, I mean, three important problems. all three are NP complete, and these are very basic problem coverage problems that I think you should know all of them. So somehow the input and output of them are almost the same. And we talk about all three of them, but let's start with the first one, which is a set cover. And we talk more about set cover here. So this, all of them, there are several versions, essentially. You can consider the weighted version, unweighted version, but like even the simplest unweighted version is interesting. So here you have, in the set cover, you have a universe, E1, En of n elements. And a set of, and this is a collection. Collection is a set of subsets, essentially. So we have a subset of U. And then what is the job is that you want to find, and so we know that this universe is just union of all elements. So each element appears that is in one set. And here, there is also a cost function. I mean, for each set, how much is the cost of this set? Even you can consider this cost is one. That is the problem is interesting. You want to find a sub-collection S prime of S such that S primes covers U. What's the meaning of coverage? It means that the union of all those elements, all those subsets that you have selected, essentially with the whole universe. This is the main condition that we have. And of course, as I mentioned, each set has a cost. We try to minimize the cost. And there are some other versions of that, more things like the submodular, that this cost function is not additive, is submodular or subadditive or other type of thing that you can consider. But this is the basic one, which is additive, essentially. So there is another problem. I mean, this is very similar to this one, and we will talk about this problem today, set cover. And this is, in general, this problem is log n. There is a log n approximation for it, and log n approximation is tight for it. And we talk about the algorithm that we have. A second problem, which is very important, is the unique coverage. So that's actually the one that we invented. I mean, like this current version of it. The input is exactly like set cover. So you have a universe U, and you have a subset of sets as a collection of this U, and say you know that the union is equal to, like, essentially the union of all these sets would be U. What is the objective? You want to find a sub collection, again a subset of S prime, that maximize the number of elements covered by exactly one of these guys. So this is the unique coverage. And why this problem? So you want to essentially the same input. You want to select essentially some of these guys such that you maximize the number of elements that are covered by exactly one of them. So in the previous case, you want to find the minimum number of sets if the sets are unweighted. Here, it's a bit different. You want to, here you can also consider the case that we have a cost and cost version of, but in the simplest form, you just want to select, you don't care how many sets you select. You want to maximize the number of things that are uniquely covered. And all of these are very important problems. This set cover almost in any practical application appears essentially as an important problem. Unique coverage is also a super important problem. And one thing that this problem is become very important, essentially, when you try to design such that you want to maximize like areas with no interference. So what is the idea? So the idea is this one. So say you have, this was the application. This was the paper that we had it with Uri Feige, Mohammad Hajiaghayi, and Eric Demain, I think in SODA 2006. And the motivation came from, actually some person from Bell Labs mentioned to me, and then I formulated the problem. So the problem is that you have some of these antennas, and you want to, and these antennas, each of them are covering some areas. Good. And So whenever like some area like this is covered by two things, there is interference. But the areas that are covered only, and of course, the area that they don't have essentially covered by anyone, then there is no coverage. So what are the best areas? The best areas actually are these areas that are exactly covered by one element. Here, this is by one cover essentially. So what's the meaning? What's the meaning of this unique coverage? The simplest form is this: that you want to just turn on some of this tower. Maybe this tower, I mean, is just intersecting too much with others. You don't want to even turn it on, such that you will maximize the areas which are uniquely covered. These are the areas that have essentially coverage, but they don't have any interference. So this is the unique coverage. That's actually motivation. But then it has application in MV pricing and lots of other things. They're very important things that I talk more also about it in this other course, algorithmic lower bounds. That, by the way, actually, if you go to my YouTube, I'm uploading the lecture, the essentially videos of that course as well, so you can take a look at it, and you know more about some lower bound for these problems. Good. Now, the third problem that we want to talk about is the maximum coverage. So what is the maximum coverage? The maximum coverage, again, the input is the same as before. You are given essentially a universe and a set of sets, essentially. Here, the goal is that, and again, you can consider that each set has a cost, essentially. And here, there is also a cost bound B is given to you as. What is the objective? You want to find, again, a sub-collection that, and you can here, again, you can consider a more general version that each element has a weight as well. Some kind of a knapsack type of things. So you want to select a set of sets such that their cost is at most B. So the cost is at most B, while maximizing the sum of the weights of some of the weights of covered elements. So that's the objective. You want to find essentially, you can also consider the case all the weights are one and all the costs are one. Even the problem is NP hard in this case and the algorithms are non-trivial. So you want to just find essentially at most, say, k-sets, weights are one, such that you maximize the union of the size of the unit. That's the maximum coverage problem. Again, this is why is it important, because of the same network design that I mentioned. So maybe at some point he said, okay, having coverage is better than no coverage, even though you have interference. So how can we maximize the area essentially? And you have some budget to create essentially or rent this kind of tower. So you want to essentially build some of them or rent some of them such that you have maximum coverage. And that is actually interesting also. This is some of the advertisements, like they were talking, I think for Verizon or T-Mobile or others. They mentioned actually we have coverage for 99% of Americans. And that is interesting. They don't say that 99% of America. They say 99% of Americans, because they said there are some areas that nobody lives there, so we don't cover them. And this actually maybe big areas, but generally there are not too many people there, so they can essentially say that these are noise, we don't cover them, but the rest, the areas with lots of people, essentially we cover it. So that's again, so these three important problems, all of them, the input, I mean, the simplest way you can think about, we have a universe, we have a set of elements, and we have a set of sets. We want to select a set of sets to maybe cover the union BS, the minimum number of them, or you want to maximize the number of uniquely covered elements, or you may want to actually just, we want to select K sets with the maximum union. And these are the problems that we are talking today. And these are like important, very important problems, essentially. And of course, for set coverage itself is that this is the other rule, for example, that they had it. I mean, before that, like, for example, one of the, this was again some rules, I think probably before 2000 or something like this, that this was the rule that AT&T and Verizon actually were part of the one company. And then, but they become essentially two companies. And then that was the idea, is that each state should be covered at least by one of them when we are talking about essentially long distance phone or, like, for example, internet coverage, etc. And because of the rules, so if you are AT&T, if you are, this is a state that you need to cover it, you need to cover all areas. So in that sense, essentially, you want to create a minimum number of these kind of things to cover the whole area. This is a set cover, essentially. So in this case, you don't have a choice. You need to cover everything, but you want to minimize the cost. So these are all very basic network problems or network design problems. And let's, so we will talk more about them in this session. So, like, we are talking a lot about approximation algorithms here, and this is, I mean, just to remind you about approximation, we always talk about some like opt is very important. Opt is some kind of adversary. You can think about opt is some kind of um, solution that God gives us by any definition of God. And then and we may not know that, but generally in approximation algorithms, we want to get, say, this is dependent, I mean, what type of approximation algorithm, but in the minimization set of approximation algorithm, we want to find some solutions that, of course, it cannot be less than the cost of opt, but you want to make sure that at most they are alpha times cost of opt. And this alpha called alpha approximation. And this is for the cost that we try to minimize. But sometimes we talk about some other things like value that you try to maximize. This is the maximization problem. So in this case, we say that the solution that you obtain essentially, so your solution should be between the value of opt, cannot, again, better than our value of opt, and should be at least alpha times value of opt. So in this case, alpha is less than 1, and we call it alpha approximation. However, I mean, the maximization problem, sometimes actually it is very common to talk also, when we talk about approximation, we talk 1 over alpha. For example, if the result it is like half of the, or I mean, you can change this formula and say that instead of that, instead of alpha times this, we can just, instead of alpha, I will put it 1 over alpha. If I say 1 over alpha is that, so in that case, if you have 1 over 2, like, for example, the value is half of the things, we call it 2 approximation. So in this case, both alphas would be greater than 1. In generally, we are very happy to say that alpha is greater than or equal to 1. So that's the, so because when you talk about approximation and the approximation factor becomes less than half, less than 1, maybe does not mean that much essentially. What's the meaning of I have approximation which is better than 1? That's the reason that the people try to get essentially the always greater than or equal to 1. It means that 1 means optimal, greater than 1 is that you are far from optimal. But if it is 1/2, it's not far from optimum. It's actually very close to, even is better than optimum. Good. These are some of the examples that I have mentioned essentially. And again, all the lecture notes, both my handwritten notes and these are that are essentially typed in LaTeX, all of them are available from the course website. Just go to my homepage, network design, the latest network design course, and then you will click on it and you will find it. And as I mentioned, these applications of these 3 problems. Now we want to talk more about set cover problem. And the approximation for that, we will continue for this maximum coverage and unique coverage in later sessions. Good. So let me just define this if whether we have defined it. Good. Good. So here we are defining this term if for the, so we are talking about set cover, and for set cover we have let's define the frequency of an element. So this is the element in the universe U. So this is an element E belongs to U. So for such E, we say that f or f of E. So f of E is the number of sets that this element appears. So that calls f, frequency of this element. And then f is the maximum frequency over all elements. So what is f is the like the maximum number of times that one element, any element, appear in the or sets. So that is f. And here I wanted to give a approximation algorithm for these problems. So what do we provide here? We are providing here an algorithm. We say that there is a minimum of log n and f approximation for set cover. And n, by the way, was the number of n was the number of elements. So n was the size of U. Just make sure that it is the case. Okay. So n is the size of U here. And we are giving mean of, so this is the mean of f and log n. As I mentioned, n is the size of, we give minimum of this approximation for the problem. So what is the greedy algorithm? This is actually, these are like somehow beautiful, the analysis. And there are other alternative approaches, but these are very fundamental and it is important to know because you can actually extend it for lots of others. So what is the greedy algorithm for this problem? So we are like, we are starting with C. C is the number of, C essentially is the set of covered elements so far. So C is the covered elements so far. So C originally is empty because we have not covered anything. And we will say that while C is not equal to U, while we have not covered all elements, what should we do? You will find set S with the most essentially cost effectiveness. Or among all the sets that you have, you will find the most cost effectiveness. What's the meaning of the most cost effectiveness? Is the one that minimizes this parameter alpha. So what is the parameter alpha? So for each essentially alpha for each set S, alpha of S is defined to cost of S over S minus C. So what's the meaning of that? I mean, cost of S, of course, is, I mean, the cost of S that is given to us, you can think about it is one even. S minus C is that how many new elements this set covers. Defines this parameter essentially alpha for this, and like alpha of S, and we are taking a set that minimizes these things. It means that a set that minimizes cost per new element covered. That's the set that we are doing that. Now, what do? We will pick that S. And here, this is the part, actually, it is for the sake of analysis. So what do we do in terms of algorithm? This is somehow in parentheses. So you will pick S, you will add this, all the elements, new elements that are covered to C, and then you will repeat this loop until you cover all elements. So this is a simple algorithm. Find the most cost-effectiveness. A cost-effective set means that for this set, the cost per new element is minimized. Add that set to S, add the covered elements to the set C, and then repeat this one. And then output the picked sets at the end. However, for the sake of analysis here, we are also adding these things. It is not really needed for implementation, but then we are picking S for each element, for each new element that is covered by S. This is the meaning of new elements. So for each new element covered by S, I put the price of these elements equal to alpha. And that makes sense. Why? We say that, okay, this is the cost of S that is somehow amortized over these new elements. So I will give each of them the cost that I pay to cover. And this is alpha for this. This is for the sake of analysis. One important property of this one is that the cost of this greedy algorithm that we have, it is a greedy algorithm. Why is it greedy algorithm? Because at each step, it just chooses one set and does not change the choices. Otherwise, it was some kind of backtracking or branch and one. So just choose this one and doing that. And this is the cost of, this is the greedy algorithm. And this is equal to some of the essentially price of E sum over all elements E belonging to union. So essentially, the total cost that we have paid is equal to the price that we paid for all these elements, because by definition, essentially. Since the set cover, is a very supernatural algorithm. I think they will attribute it to Lova's greedy algorithm. But anyhow, at that time, probably, lots of other people have been there. Also, they could, consider this algorithm. So the analysis is a bit non-trivial. Lots of this kind of greedy is a good thing for heuristic. But the fact that the beautiful thing about this algorithm is that this is the log-n approximation that gives it, and you cannot do anything better than that, essentially, by a hardness result, unless P is equal to NP. So this is this one. So let's go to the analysis and see how does it work, essentially. Why this is a log-n approximation. Good. So I wanted to see, so this is the main claim that I wanted to do. I want to say that, so say we are running this algorithm, and at some step we have a current set of C of the covered elements. So these are the covered elements. Now, I want to say that there should exist a set S such that its cost effectiveness is at most, so for this, the cost effectiveness is at most size, like essentially opt over U minus C. What's the meaning of that? Whenever we talk about opt here, so sometimes we talk about opt as the algorithm that finds the optimum algorithm. And this algorithm may take exponential time. But also lots of the time we are using the same notation. When we say opt means cost of the opt, whatever, or value of the opt, or whatever objective that opt has. So here we say that there's, at any time that we have it, there is one set S such that the at least the cost effectiveness of this set is opt over U minus D. U is the total number of elements minus those elements that I have. I want to prove this. This is very important. And this actually, the things come from this fact mainly. Good. So the proof is by contradiction. Assume that it is not the case. And we will essentially get some contradiction. Consider the optimum solution. The cost of optimum solution, and say these are in the optimum solution here. So here, when we talk, we are here, as I mentioned, we talk about opt as an optimal algorithm. When we talk about opt sometimes as an optimal solution, what is the solution? And sometimes we talk about the cost of it, opt. Here we consider opt as the solution that we have. So this opt essentially has in it S1, S2, to Sk. These are the sets that are in the optimum algorithm. Good. There are K sets that optimum somebody computed. Okay, so I want to say that actually one of these sets, of course, here, the algorithm will find the most cost-effective set. It might be something even below the cost-effectiveness of these sets that I have it. But I want to say that if you just consider S1 to Sk, there might be some other sets. At least one of them should have this cost-effectiveness. So this is the one. At least, so I just said that just consider opt. Again, we don't know what is opt. Say that somebody is giving opt. These are the things that we are essentially. So this is, we always do this type of thing in approximation algorithm, that we consider optimum and we will massage optimum. And then we get some properties of optimum, and then we show that actually we have a good solution. So here I'm considering optimum. I don't know what is it. This is some existential things essentially. Or you can compute it in exponential time. So this is S1, S2 to Sk. And I want to say one of these sets have this cost effectiveness. Let's say what will happen if it is not the case. So we know that the cost of opt is equal to cost of S1, cost of S2 to cost of Sk. So that is this. So I will just write, instead of cost of S1 over S1 times S1. So this is our equality. I will just write it down, this. So this is the equality that we have here. Now, what do I have it here? I will consider alpha to be the minimum cost effectiveness of these sets. So alpha is essentially the minimum cost effectiveness of sets in opt. So this is the current alpha. And we know that the alpha that we will choose in the greedy algorithm would be less than this, because then we have more options among other sets which are not in opt. But we know that, so in some sense, maybe we can call it this alpha, the other one is alpha prime. Or maybe we can call actually this one alpha prime. That should be fine. Alpha is, say, the minimum cost effectiveness of all sets, and alpha prime. So then I need to put here alpha prime essentially. And we know that alpha prime would be greater than or equal to alpha. Good. Now, by definition, so the cost effect, this is the definition of cost effectiveness of set S1, the cost effectiveness of set S2, and so on and so forth. So that would be greater than, and alpha is the minimum of them. So this would be greater than or equal to alpha times size of S1, alpha times size of S2, and alpha times Sk. Good. Oh, one other change that I want to say. So when I'm talking about, we are talking about U minus C. So these are some of the elements that are already covered. Those elements which are already covered I will just, so this S1, S2 to Sk, I will actually call them also S prime, maybe S prime 1, S prime 2 to S prime K. Why do you call it prime? Because I remove those elements which are already covered. So essentially this sets in the opt that I remove those elements that I have already covered. Now, but still the cost, I don't change the cost. I'm just talking about, so I'm somehow changing these elements such that those elements that are covered are, because they are not part of the things that I know that this now, because opt covers everything and I just remove some covered elements from that. I know that if I remove this covered element from each of these sets, still these reduced sets, they should cover the rest. What is the rest? It means U minus C. So it means that S1, size of S1 plus size of S, some size of S1 prime, S prime 1, S prime 2, and S prime K, that should be at least U minus C. So what is the things done, I think, from this one? So we just prove that essentially the cost of opt, or essentially opt, we will call it again, abuse of notation, would be greater than alpha prime times U minus C. So that means essentially the alpha prime, so that you can just bring it here. So alpha prime is, sorry, just, so this, it means that I can just essentially change this one from here, and I can just bring it to here. So it means that alpha prime should be less than that, and we know that this is also greater than alpha. Because alpha is global minimum, somehow alpha prime is local minimum. Good. So we show that essentially always there is a set among the remaining sets such that its cost effectiveness is this one. And now we are almost done. So this is the one that's so far we have done it. So this is essentially the main thing that we need. Let me just clear everything. So this is the main thing that we know. There is one set that has this problem. Now let's try to just analyze the whole algorithm. So cost of the greedy algorithm is equal to sum of the prices of all elements. That's by definition, as we have mentioned. So it is equal to price of E1, price of E2 to price of En. And then you can actually name E1, E2, En according to the, so what is E1, E2 to En? These are the elements that are covered by algorithm one by one. So, and when you have essentially a set, you can just break, you can do some tie breaking. So essentially, the first set of EIs are the one that we are covering first, and then the next batch is the one that we are covering with the second set, and so on. But we can call it E1 to En. Now I wanted to just essentially do these things. So here, what is the price of E1? The price of E1 would be essentially alpha. Good. So just let's see at the beginning. So we know that at least, so here at the beginning, so C is equal to empty set. We have not covered anything. So this says that there is at least one which is opt, there is one thing that, so alpha would be less than opt over size of U. Good. Now, in this case, so you say you are finding a S that, for example, it has in it E1, E2 to EK. So this is S is equal to this. So these are the set of elements that, this is the most cost effectiveness. So each of them, so here, this essentially the price of E1 would be alpha, the price of this would be alpha, and so on and so forth. Now, let's do this summation. So we know that the price of E1 would be, I want to just replace this size of u. I know that for E1, E2 to like Ek, all of them, the denominator is u, which is in this case n. If I reduce this denominator, for example, from n to n minus 1, then just this is the upper bound. So at the beginning for E1, so for E1, the cost is alpha. So so I will just use essentially this formula. So I will say for E1, the cost of it would be cost of opt over n minus 1 plus 1. Of course, n minus 1 plus 1, this will cancel, would be opt over n. So for E1, we are essentially getting exact price. Now for E2, we know that its cost would be opt over n. Here, what would be here? It would be cost of opt over n minus 2 plus 1. It would be n minus 1. So instead of n that I have to opt over n, I have it opt over n minus 1. But that just essentially, that would be an upper bound, and that is fine. So then we will essentially do that for all of this. The k guy would be, so the next one would be, that would be, the cost would be opt over n minus k plus 1. So I just essentially decrease the denominator, that the cost goes up. And again, so after S that we have selected it, the same thing essentially happens. Now, this was the first set that we have selected. The same strat, the things happened with S, the second set. And again, you can say that at that time, now say what would happen in the next time. In the next time, we have another, so we have some C which is not empty anymore. So it is. So in that case, you can again say that the cost of the first element on that set, the cost of it would be opt over u minus c. So this is like opt over n that we have mentioned. So for that one, we exactly capture the actual alpha. But again, for the remaining elements, by this formula that we are decreasing the denominator one by one. We are just giving an upper. And again, in the worst case, it can happen. If there is only one element in the set, this inequality would be exactly equality. Okay. So we know that this is equal to price of E, and which is this, and this is less than this thing that we have computed. And this is essentially, this part is the one that I have described here. Why we have this formula. Now, and okay, so then we will do it. So this is the last one is En. For En, this n and n will cancel, would be En over 1. Now, here we have cost of opt over these things. Now, I can just factor cost of opt, and then the remaining things would be essentially here would be, as I mentioned, this would be 1 over n minus 1. So this would be n minus 1, and so on, so on and so forth. The last one would be cost of opt over 1, which would be 1 essentially. So it would be cost of opt times this, and this is exactly the harmonic number, n's harmonic number. So it would be cost of opt would be times ln of n. And this is interesting. Actually, this algorithm gets ln of n, and we know that we cannot get anything. The people even worked on this parameter, the exact approximation factor, and there was something. I think, if I remember correctly, the latest one says that you cannot, if you can get anything better ln of n, you cannot get anything better than ln of n approximation for the problem unless p is equal to p. So even the people, this factor, because you can consider log, but the log might be in different base, so it has a different constant. The people even work on the constants. Exactly ln of n is the best that you can get. It beyond that would be not even a constant factor below. That is the hardness that currently exists. So it is a very tight thing. And at the same time, there is a this one that I have mentioned is a tight example. So here we don't, as I mentioned, there is no better than ln of approximation, but there is a case that actually this algorithm, this greedy algorithm, pays ln times cost of opt. So what is this? This is actually a very nice example. Again, appears in lots of things. These examples especially are important because it may apply for your own problem as well. So what is the example? Consider this set. So we have n elements, and these n elements are even like 1 to n. Now I have n plus 1 sets. I have n plus 1 sets and n elements. So n elements E1 to En. What are these n plus 1 sets? So the first set, there is one set that contains the first element, one set that contains only the second element, and so on and so forth. N set that contains only the nth element. The cost of, okay, what are the cost of the first one is 1 over n. What is the cost of the second one is 1 over n minus 1. And so on and so forth. So the last one, the cost is 1. Then there is another, like n plus 1 set, the last one, which contains all of them, and the cost would be 1 plus epsilon. Good. Now see what will happen. So here you can see actually the optimum. I mean, at least optimum would be less than that, but it's actually exactly equal to that. If I just choose this S star set that contains all of them and the cost is 1 plus epsilon, then the total cost that I will pay is 1 plus epsilon for opt. Opt is equal to. You can just only say opt is less than or equal to this, but opt is actually equal. What does the greedy algorithm is doing? So the greedy algorithm comes among this set. So for the S1, what is the cost effectiveness of that? So it covers essentially the cost of that is 1 over n, and it covers one element. So the new elements that are covered. So the cost effectiveness of this would be 1 over n. What about the S2? The cost effectiveness of S2 would be essentially 1 over n minus 1 over 1, which is 1 over n minus 1. So the cost of the second one is actually more than this. So far the first one is good. Let's see what is the optimal guy. The optimal guy essentially pays 1 plus epsilon, the cost of everything, for n elements, which is greater than 1 over n. So the greedy algorithm first chooses S1 and pays 1 over n. Now what will happen for the second element? For the second one, then now we'll consider S2. S2 again covers one element, and the cost of that would be essentially 1. So it would be 1 over n minus 1. So 1 over n minus 1 over 1 element. This is the cost of S2, essentially cost effectiveness of, which is 1 over n minus 1. Again, you can see that all others would be greater than this. What about for S star? S star now covers how many new elements? N minus, here, the cost of it is 1 plus epsilon. And how many new elements it covers? Essentially n minus 1, because 1 covered. So this is greater than 1 over n minus 1. So in that case, again, we are choosing S2 instead of the optimum. And so on and so forth. So the total cost that we are giving actually would be 1 over n plus 1 over n minus 1 plus 1 over n minus 2 and 1. This essentially would be h of n, which is ln of. So this is one example actually that at least this algorithm is not good, but you can show that actually there is no algorithm no algorithm that can guarantee anything better than this, unless p is equal to, that you can solve the problem. Now, we talk and we mentioned that, okay, we are considering this, that we talk and we mentioned that there is essentially there is a mean of f and ln of n, or log n approximation for the problem, for set cover. We talked about ln of n, let's talk about f. And again, f, what was f? Was the maximum frequency. Frequency of an element is the number of times that one element appears. One element appears, the number of times that a set contains a particular element. And f is the maximum. So what is the, this is essentially a greedy f approximation for the problem. Another greedy algorithm. What does it do? So at the beginning, the cover of A is equal to empty set. So we have not covered anything. This is essentially like C. So again, so this cover of A is essentially C. So that while essentially there exists one element E that is not covered. What do? We will, this is the main important thing. While, so there's one element that is not covered. We have not ended. Otherwise, we are done. There's one element which is not covered. Add all the set that contains this element. So this is a bit counterintuitive. So we don't add just one set that contains this element. We are adding all the sets that contain this element. And this is important again. Somehow it seems waste of time. Why do we need it? For this guy, we can cover it essentially with one set. Why do we cover all sets that have it there? But there is a essentially trick that we will talk about. Good. Good. So what do we do? It so this is the cover. So at any time, if there is a so we have this universe U, and then this is the cover. If there is one element which is not covered, you will add all the sets that contain this element to your solution, or remaining sets. And also we will add, say this is contains an element E. So we will, this E, we will also add it to U prime. So U prime is a subset of U of those elements that are not covered. This is the algorithm. Very simple algorithm. Now we want to say this is the F approximation. So the proof actually is, I mean, beautiful proof, very simple again. So this problem, I mean, these are the proofs are essentially very simple and it's very interesting. But the issue is that if you need to think it right way. If you don't think the right way, it can be actually quite complicated. So what is the proof for this one? So the whole idea is come from U prime. U prime is those elements you see. This is the first element that is not covered. Then the second element that is not covered. So I will add this one. So and then say this has E1, E2, we'll say EK. I will say that these elements are independent. They form an independent set. What's the meaning of that? It means that no sets can cover two of them. But this is somehow essentially this is single P and then yeah. So and so in some sense here we want to say this is the idea is that no sets can cover two of them. Right? This is by definition because when we consider E1, we added E1. We added all the sets that contain. So if E2 is not covered, it means that those elements, those sets, that we have chosen, they have not covered this one. And so there is no element that contains E1 and E2 essentially. Otherwise, it was covered up. So it means that E2, there should be no set that is covered. The same thing you can continue. Now E2, now you will say E3. If one of the sets that contains E1 and E2 contains also E3, then we have already covered this guy. So by definition, E3 also is not covered by this. and so forth, so on and so forth. So it means that there is no set that can cover two of them. What's the meaning of that? It means that optimum, and by the way, this is one other thing. So here we are assuming the cost of each set is at most one. That we are using. So all the elements have the same cost. All the essentially all the sets have the same cost. This is the secret. So we know that no element and no sets is covered two of them. So it means that optimum needs at least the size of U prime. So we know that opt is greater than or equal to U prime. And again, this is on the cost of each set is one. Correct? Because no set can cover them. How much did we pay? We paid exactly F times U prime. Because each of them had at most, the frequency of each element is at most F. So at each time we have added F sets essentially. So that is cost of algorithm. And this is opt, and then this is the F. So this algorithm works when essentially the case that not arbitrary cost we have it, all the costs are one. Does it work essentially for case that the costs are different? No, it should be all the things should be actually the cost one. So this is I will say two exercises I will say that is actually good for your final exam as well. So the first one is that, I mean, say y is not working. So y not working. Why not working for cost version? So that is one thing essentially that if they have a different cost, then it might not work. The second, this is interesting. So the example that I have mentioned for the greedy algorithm, that is a ln of an approximation, the cost of the sets were not one, or they were not uniform. We have a different cost for different sets. Create a hard instance for set cover for log n approximation for ln approximation with all costs one. Good. So all the costs should be one. It's essentially the uniform case. Whenever the costs are one, we call it uniform. The same, we call it uniform. Can you create this log n when the costs are one? That would be two exercises that you can actually do it. You need to change that example because the current one is not working. But you see whether can you create it maybe with some repetitions or other things. That's a good exercise actually. And then why this algorithm does not. Now, if this algorithm is not working, then what can we do if the cost are? So then essentially there is another F approximation algorithm by linear programming. And we are using linear programming a lot essentially in this class. And we may talk a little bit about it as well. But here, we talk more about linear programming, but here it is relatively simple. So we just write essentially this problem for these things. Let me just clear all of it. Good. Okay. So how can we show that actually this is a good algorithm? So let's, essentially write the constraint that we have is an integer program, and then we relax it to a linear program. So what do we want to do? So x here we have a variable xj equal to 1 means select a set. Select sj essentially. And xj equal to 0 means not selecting it essentially. Good. So you want to select a set of sets. For those that you are selecting, you will equal to 1. The rest would be 0. And these are for all elements. So what do we want to have? Good. Now, of course, we want to minimize the cost of those guys. So if xj is equal to 1, we want to have essentially the cost of, okay, so here actually, what is the cost of sj? So it means here the cost of sj times xj. So that's essentially this is the cost of xj essentially. So cost of xj, you can think about it like this. So you want to minimize essentially some of those elements that you have selected, those sets that you have selected, times the cost of them, 0 for others. The only condition is that what's the meaning of that is one element is covered. One element is covered, you can write it this way. You will say for each element, essentially, I equal to 1 to u, all those over all those sets that actually, so here I will say I actually belongs to sj. So if I belongs to sj, if that set contains I, sum of the xj of those guys should be greater than or equal to 1. Essentially means that among those sets that contain this element, sum of the xj, one of them should be selected. So far, this is the integer program. If we are assuming that the values are 0 and 1. And so if the values are 0 and 1, then of course we are in a good shape here. And this is exactly the set color problem. And this is the integer program, so we cannot solve it, of course. But we can relax it to an integer, to linear program, essentially. And this is, by the way, integer linear program. Why? Because all the constraints that we have are just like cost of this sj, which is a constant, times xj. So everything is linear on terms of these variables. Now, I can get essentially relax this integer things, and I will say that the xi's all, instead of be 0 and 1, there should be between 0 and 1. So that means the relaxation of this LP, and relaxation means, I mean, then the solution, this is called a linear program or fraction, because the solution now can be fractional. So xi now can be, instead of between 0 and 1, it can be half, it can be 1/3 or any number. And then, of course, in this case, the issue is that this linear program, we can solve it in polynomial time, fortunately. But the unfortunate thing is that if the xi becomes essentially 0.21, I don't know whether it should be 1 or 0. That's the thing. So this is the relaxation. That's the thing that we need to round this linear program. Rounding means essentially these variables from anything, as I mentioned, it's anything between 0 and 1, you should make it either 0 or 1, because that's the solution that you should give at the end, an integer solution for this. And but anyway, you don't to say that xi is less than or equal to 1, because by definition, we are minimizing this one. You can check that you need to put xi greater than 1, because as long as you will put xi equal to 1, you satisfy this for all things that you have it. And if you put xi greater than 1, you just increase this cost. So nobody will do that. So the cost, actually, you only need to say that xi is greater than or equal to 0. So this part is not really good. Now, given that, let's see again, when you write this LP, so this is the LP that we are writing it essentially, and again, this one, cost of SJ times XJ, and this one was SJ. Now I want to say this is a F approximation. So how can I get a F approximation? So consider an element I in the solution. We know that at least one of these xj's that this guy belongs to that should be at least 1 over f. So in the fractional case, at least xj, at least, let me just, so let me say this one as well. So for any element I, at least uh, for one set Sj that contain I, x of j is greater than or equal to 1 over f. Why is it the case? Because of these conditions. We know that for each element I, some of those variables that some of the xj, for those guys that this guy belongs to that, should be at most f. It should be at most 1. How many sets are there? There are at most f, because the frequency of this guy was f. So one of them should be greater than or equal to 1f. Then what do we do? So we will consider the first element, say. We know that one of these guys is greater than or equal to 1 over f. We will select that set. And of course, those elements that this set is covered, all of them will be covered. And then we repeat the same thing. We don't need, this is also another interesting thing, you don't need to solve this LP again. You can continue with the same LP. And you will essentially continue. So among those sets that this sum of this xj should be, for one of them should be greater than 1 over f, and then we will select these sets with all elements, and then if there is another non-covered elements, you are doing the same thing. One of those sets should be greater than this, we will continue and do that. Now, this is the F approximation. Why? First, we know that we had originally these xj's are between the xj's are between 0 and 1. When we, instead of 0 and 1, we know that when this is a minimization problem. When you relax it, the solution of the LP, this objective here, is less than or equal to opt, the original opt, because that's the integral. This is, you have essentially more conditions on opt than here. So it is between 0 and 1. Here it was. So we know that the objective or the LP solution is less than opt. How much is the cost of us? So anytime we know that LP paid 1 over f, we paid 1. So our cost, the algorithm cost, is at most, so alg cost is greater than f times objective. And note that, here the LP pays cost of Sj times Xj. We are paying also cost of Sj times X. But here it pays maybe 1 over f there, but here we are paying 1. So there is a factor, essentially f here difference. So we know that cost of our algorithm is at most f times the cost of objective. So the cost of alg is at most f, and objective is less than or equal to opt. So what's the meaning of that? It means that our algorithm, this we can say that essentially, yes, so the cost would be, sorry, that is wrong. That would be less than or equal. So our cost would be at most f times, because LP pays at least 1 over f, we pay 1. And then we, of course, we know that this is less than f times opt because of the previous. So we have f approximation. We always need to compare with optimum, but this is a typical thing that you will see in all linear programs, that we will compare it with linear program and then we will connect it to opt. So in some sense, here this objective or linear program is some avatar of opt. Good. So this is essentially F approximation, and as I mentioned, so also this LP that we have mentioned here, this LP also you can round it and you get log n approximations. So not only give F approximation, but also you can get it log n approximation with this LP. And essentially the idea is, you can write this LP and then you will choose each element with probability xj times log n. Yeah, so xj is something between 0 and 1. then the probability that you will choose one element at random would be xj over times log n. A little bit you need to boost it, and then you will do it. Then you will cover something, and then you will repeat this one. This gives also log n approximation. So this LP gives essentially the best thing. And usually for the problem that there's a LP or SDP, currently these are giving the best solutions for us. So, and as I mentioned, Feige showed that, I mean, you cannot get no 1 minus epsilon times ln of n unless essentially NP has these conditions. And that's a thing that we know that. And here, so we know that this is this. There are some additional result after that. I think the current best bound is that you cannot get 1 minus epsilon ln of n. This is not p not equal to np, but you can say that even np not equal to np is enough to get 1 minus epsilon. There was something like 4 times ln of them. You cannot get it under p not equal to np, but I believe that has been improved even to ln of n. So that is very tight result that we have it. And this problem also, the set, this problem is equivalent of the set cover. Set cover is equivalent of minimum dominating set in graphs. You can, if you see the approximation algorithm book of Vazirani, actually, you can see the section 2 and 3 is talking about it, and you can see more examples. But minimum dominating set is nothing different from the set cover, essentially. And I think given that, we are finishing this session, and then we will continue, I mean, for the other 2 problems in the next session.